Hey folks, this is Major Jones here to talk to you about pipelining the LC3 version 2. So in this lesson, we're going to actually look a little more closely at how we would actually construct this pipeline, how to turn the LC3 from the processor we know it into a pipeline version. And so we're going to get pretty detailed in terms of how we need to rearrange this this processor and where signals are going, and hopefully by the end of this, you have an understanding of pretty much at the circuit level what a pipelined LC3 looks like. So let's get started. To review from our last lesson, right? This was the last lesson on pipelining. We have these. We were able to sort of separate our LC3 into five stages, right? Fetch, read registers, evaluate address, and sort of execute phase, where we either access the ALU or memory, and then writing to registers. So we're going to see that basically those stages kind of crop up here in our detailed diagram. And I think it's honestly easiest to kind of start with start building this pipeline up sort of an instruction at a time. So we'll start with our three of our operate instructions, add and not, because I feel like those are conceptually the easiest to kind of wrap our heads around. And so what we know is, if we're starting with the fetch phase, I've got a register that holds my program counter, and so that's going to, that address is going to go to my instruction memory, and out of my instruction memory is going to be the instruction that I'm reading. We'll assume it's one of these three, right? Add and not. And so that instruction is going to go on to the next phase, read registers, and then at the same time, I know I need to increment my program counter. So for right now, we'll just say that we're automatically going to increment by 1, so that value comes around here, and it's set up and it's ready to get loaded into the program counter on the next clock cycle. When my add or and or not instruction goes to my read register phase, then sort of two things happen. One is that whole instruction goes to this block of logic here. That's my control unit, which generates the control signals for the rest of the LC3 in order to execute this instruction. And then I've got two parts of my my instruction that specify at least source register 1 and potentially a source register 2. I don't know if I'm going to need this just yet, so I also send the full instruction on to the next phase. So you can see here kind of 4 signals moving onward from the read register phase into subsequent phases, which are any control signals I need, the instruction, the whole instruction itself, and potentially the register values that are coming out of my register file. Now, for these instructions, nothing really happens in the evaluate address phase. So these signals just go straight through. They go straight through into this phase here, fetch operands, which is a new one for us, because I felt like if we're getting detailed into the detailed design of the LC3 pipeline, we're going to reintroduce the load indirect and store indirect instructions so we can get a better understanding of what this LC3 is doing. So we're going to reintroduce this phase. Add and not don't use fetch operands, so they move straight through the fetch operand phase into my execute phase. Here you can see I've got my ALU. I've got source register 1 that goes into the A side of my ALU. The second operand here on the B side is coming from either SR2 or some portion of my instruction register. And what's not shown is that the instruction register, the bit 5 in here, is the thing that tells this SR2 mux whether it's taking the SR2 value or some immediate value. So not quite shown here is that control signal. And then coming out of my execute phase will be the results of my ALU. I sort of continue onward with my control instructions, my control signals, those go through this phase. And then I've got a portion of my instruction register that goes into the last stage to write a register. So here I've got the other portion of my register file, which is, has the destination register being selected from the instruction. So DRA stands for destination register address. And so this is the DR field for my instruction. And then DRD is destination register data. This is the value being stored to that destination register. And that's coming straight from my ALU for and, add, and not. So then this pipeline here kind of shows you how we might construct the components for these 3 instructions. And I'll just point out here that, this component right here, where I was reading registers, and this component here where I'm writing registers, they're the same component, right? They're shown with a little kind of sawtooth on the top and bottom to indicate the fact that they go together. And like you may have seen in the note from the last lesson, this is allowed to be one component, and there's no structural hazard by virtue of the fact that I have these separate read ports and write ports, so I can both read and write to the register file at the same time, even if it's a single component, and so that lets me put it in sort of 2 stages in my pipeline without any sort of structural hazard. Okay, so let's keep building up this pipeline here. I feel like the next kind of most logical thing is to work with our load and store instructions. So all 3 of our loads, all 3 of our stores, we're going to build off of, you can see here in green, that pipeline that we just sort of built, and the new stuff we're going to add in purple is going to let us execute these types of instructions. So for my loads and my stores, I've got normal load store, I've got load store indirect, and load store register, right? So for my normal, let's say my normal load store, right? Let me see if I can pull up my instruction list here. Okay, normal load store, right? Destination register or the source register gets added to some sort of offset. The PC gets added to the offset, and then that value in memory is either goes into the destination register, or in the case of the store, right, the source register gets put into that spot in memory. So what I have to add here for my evaluate address is my adder and the address 1 mux and the address 2 mux from that little portion of the control unit. And so nominally, I'm going to need to send my program counter here into this phase here to be added to some offset, right? So I've got to break off my instruction register again and kind of send it down here. This signal here and this signal here are the same. So I mean, I don't necessarily need separate wires for that, but I didn't want to have to like kind of draw wires all over the place, right? So conceptually, this signal is the same as this signal, but and then the PC gets added to some offset. That's going to go through the fetch operands phase into my execute phase, and that'll become the address here into my data memory where I am either reading or writing something. If I'm writing something, that value is coming out of SR2. So then that sort of selects that becomes the value being written. And so if it's a store instruction, then I'm done in this phase. If it's a load instruction, then the address here selects which piece of memory is being sent to the data port, and then that is follows through here into the write register phase. I got to add a multiplexer now for my destination register data, and then that would be written to my destination register, right? And so again, not shown right are the control signals that select for this multiplexer, that select for this multiplexer, that tell the memory whether it's reading or writing. That's sort of assumed, and it's left off to kind of keep this diagram as clean as possible, right? Okay, if I'm doing a load store register, all right, then I've got an offset which needs to get added to a base register, and then either put into a register file, or register file gets put into it, and so I have my program counter again, I've got my offset down here being added to a base register, which is coming out of SR1. And then in the case of the load register, right, those are being added together. That becomes the address to my memory. The data gets written to the destination register. Everything's kosher. I got a little bit of a hiccup if I try to do store register, right? Because I'm going to try to pull my base register out of here. I'm going to add some offset. That's going to go here. It's going to be the address. And then the store register instruction will be looking for a value in a source register right here to be stored to memory. Now the problem with this is that if we look at our actual state diagram, to process my store register instruction, first I get the base register, and then I have to get the source register, and both of these are coming out of source register 1. That's basically both these two values here. So I'm using SR1 twice, and that presents itself as a structural hazard. So my solution to this is to sort of move the source register down here to come out of source register, whatever is the second read port, right? So we can treat this register file like it's just got a generic read port, 2 generic read ports. So if I'm doing store register, I'm going to get my base register out of the first port, and then SR, the actual source register, comes out of the second read port. So then that comes down here, and I've got to add a multiplexer here to select whether or not this read port is coming from the SR2 portion of the instruction, which is like bits 2 to 0, or the source register portion, which is like bits 11 to 9 of the instruction. So then with the source register selected, that comes over here. That piece of data is written to the memory, and I'm able to complete my store register instruction. For my load indirect, store indirect, in order for those to work, I have to not just I went to one page. I need to access memory in 2 cycles, right? I need to first I need to take my offset, add it to my program counter, get that value out of memory. That becomes the address to the value in memory that I'm trying to load from, right? So I have to do sort of 2 memory cycles, and that's why here in the fetch operands phase, this is the phase that basically is only used by load indirect or store indirect. And in order to make this work, I've got, you can see here, kind of 2 portions of my data memory, again with a little solve to say that they're basically the same component. I just have a separate, sort of read port down here into this memory that lets me process the load and store indirect instructions. So for those 2 instructions, I've got my program counter that gets added to some offset, right? The value of that addition becomes the address in memory that I look up. The value at that location of memory is now my address where I'm looking up something and either storing it in the case of store indirect or reading that value out into my register for my load indirect. So with the addition of these components here in purple, I'm able to execute my 3 loads and my 3 store instructions. Okay, let's move on. The next couple have to do with changing the program counter. So we'll start with my branch and my jump instructions. For jump, right? Jump is just changes the program counter to some register value, right? So what I need to do now is add a multiplexer in front of my program counter to select either the +1 value or some other value. And with the components I added just a minute ago to do my loads in my stores, now I've got basically everything I need to do to calculate this instruction as well. So for my jump instruction, then I just read a value out of SR, I think it's SR1. That just gets added to 0, so it goes through the adder sort of unaffected, goes through fetch operands, and then here in the execute phase is fed back around to this other input to my multiplexer for my program counter. And so then all I need to do is sort of figure out how to select the correct one, which I do with this little branch unit. So I'm going to sort of squish together some logic here that we use to select our branches up here to choose when the program counter gets a new value. And so for my branch instruction, right, I need this logic up here to sort of capture the values that's coming out of my ALU and my memory for my load instructions and my add and not instructions. So this will sort of capture, this will has inside of it basically the NZP logic and the little branch enabled kind of register that remembers when we're branching or not. And then so when I have a branch instruction that makes its way to the execute phase, then I've got a portion of the instruction register that splits off and goes to this unit and says, hey, number 1, this is a branch instruction, so the signal you send out of here is very important. And number 2, here are the signals you're looking for. So my NZP come out of my instruction, those get compared to the NZP register that's in this little branch unit, and if there's a match, then this signal that comes all the way back here to the multiplexer is selected to be a 1. Which means the value that program counter plus the offset that was in the branch instruction then gets loaded into the program counter instead of PC +1. And then this logic in here would also sort of check if there was a jump instruction, right? So if there's a branch instruction or a jump instruction, then potentially we are setting this value to a 1 so that the program counter gets a new value. Okay, so then the last 2 instructions we're going to talk about are jump service routine and load effective address. So jump service routine, we have half the infrastructure for already because the PC is going to get some some value of itself plus the offset, which is basically, we sort of set in place in here. So we just have to kind of update our branch logic to also check for a jump service routine instruction. But part of that jump service routine instruction is also to load R7 with the value of the program counter. So what we add here is a little branch off for our program counter that goes through and now becomes another input to this multiplexer for my destination register data. And I got to add a little multiplexer here for my address to select R7 in the case of my jump service routine. So when this executes, if I end up, well, the branch will select the updated program counter, and the program counter itself will get stored into register R7. Load effective address is a pretty simple one, right? We're just loading one of my registers with program counter plus offset. So whatever the PC plus offset is, the result of this adder then sort of splits off and becomes the last input to my multiplexer here to set the destination, the value going into the destination register. Okay, so then this becomes basically our completed pipeline. We're not going to talk about I think the only two we didn't talk about are the trap and the RTI instructions. And again, just to keep this thing simple, we're not going to discuss trap, interrupt, or exceptions in the pipeline. So we'll leave this as is. You can see here kind of the completed circuit separated by each of these, sort of which phase everything's in. So the last piece to do really is right at the boundaries of these stages, to add my registers. So I've got, what's this now? Five large registers separating each of my 6 stages. Right, I got my fetch portion here, read registers, which also has a little kind of control unit to generate control signals. Evaluate address, fetch operands, execute, write registers, and this becomes my LC3 pipeline. We start with the instruction and the program counter, and those get passed into the next stage. And then in each stage, I'm generating some type of signal which is sort of sent forward. It's stored in each register and then sent forward to the next stage in order to be able to execute properly. And so let's take another. The last thing we'll look at today is the control unit here, that little bubble, because because of the way this thing is set up now, I can actually simplify this a lot, right? I'm not using a processor bus, so I don't need to control which things are talking on the processor bus. So I can get rid of all of my gate signals. At least in terms of this class, if we're not having to deal with traps and interrupts and exceptions, then I can I'm not playing around with my stack pointer, my table mux, vector mux, PSR mux, privilege mode. I'm just not playing around with that for right now. So all those go away. A bunch of my load signals go away, partly because I'm not dealing with traps, interrupts, and exceptions, but also partly because I don't necessarily need to handle these things in stages, right? Part of the reason my load, I needed a load PC signal was because there were certain states in my diagram where my PC was updated and others where I didn't want it to be updated. But in the case of this pipeline, essentially, I want my PC updated on every clock cycle, because every clock cycle I want to get a new instruction. So some of those signals go away. And then you can kind of see here in the notes a couple of ones based on the way we sort of structured the pipeline. They get simplified, right? I don't have a PC mux anymore necessarily. That's selecting from a processor bus and an adder. I have that one mux here. That does select whether my program counter gets the incremented value or some evaluate address value. But I don't necessarily need that signal coming from the control unit. That's coming from this little branch unit here based on the instruction. My destination register mux only needs 1 bit to it to select whether or not the DR portion of the instruction or R7. But I do need to add a mux for my DR data that selects either the result of the ALU, the program counter plus some offset, or something coming out of memory. For my SR1, I don't really need a mux because DR or the SR1 value and the base register value all reside in instruction bits 8 to 6, but I do need that multiplexer for SR2 since I had to sort of move the source register field from SR1 to SR2. And then what that ends up being is that I've got now, what used to be, right, 42 control signals basically kind of comes down to just these 14, which is kind of nice, right? And so you can see here an example of the for the add or the load effective address instruction, what the values would need to be for the pipeline that we've laid out here in order to process that instruction. So those 14 instructions, generate they come out of the control unit, this block right here, right? I can still make this, a little lookup table, or I can make a combinational logic, doesn't matter. And then these 14 signals, are going to the pertinent parts of that pipeline to be able to set the LC3 up in each stage correctly to process each instruction. So real quick, we'll go through one example, right? SR2 is 0. That means it's selecting this actual SR2 value, not the source register value that I need for my store register instruction. The address 1, address 2 marmux, this doesn't matter. I'm not reading from memory. So this actually read-write could probably be an X, since that just doesn't matter. ALU I'm selecting for my add instruction is 0, 0. So, again, I didn't have it necessarily a control signal shown that goes to this ALU, but there is one selecting the add instruction. The instruction register itself, bit 5 selects whether or not I'm getting the SR2 value or the 5-bit offset. I do load my condition code, so that's a signal that would go to the branch unit. DR mux is 0 because I'm selecting my, I want to select my destination register that was in my instruction. The destination register data is also 0 because I want the value to be coming from my ALU. And again, there's not a load register instruction here, but there would be coming from the control unit to say, hey, load this instruction, and then that's my whole pipeline to be able to set that up correctly. All right, so this is the sort of detailed look at the LC3, which will be important for us because we're going to look at essentially this circuit for the should do them aspire to do lessons on data hazards and control hazards. That's all I got, folks. I'll see you next time.